Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Science Thursday, we're going to talk about power dispatcher. Basically the people who make sure that you have electricity in your home. So what exactly is the problem? Well, problem is that no matter how simple of a generator you make or how simple of a grid you do, electricity inherently, like electrical energy itself is unstable, meaning something will go wrong no matter what you do. Like some generator will start to go over RPM, something goes over under, some transformer will overheat, something, basically an unstable puppy. No matter what you do, it's unstable. So what is the primary core of that? The core of that is creation and consumption are not balanced, meaning you have to take a balance, you have to put consumption and you have to create creation in two of them. And as long as they are balanced, everybody is happy. But here's the real. Life is not as simple as that, so there's always this happening. And as long as you keep it as close to absolute, everybody is happy. If it goes a little bit painful but manageable, but if it goes, we did. So fundamentally, this is one of those things that works 24/7 into forever. And yes, that I actually mean that forever, meaning under no circumstances a national grid ever goes down. Like unless extremely worst scenario happens, it will never happen. That you will have like a grid, even in American grid, like you can have a small sector go down. That happens. It's very rare for a modern country, even India, to have like whole grid going down. That's very, very rare. So supply must match in demand while keeping two vectors in control. Vector number one is voltage, vector number two is hertz. Hertz is very particular, so to say, and be mindful, hertz is so particular nowadays that back in the days we had like 50 hertz. It could deviate 1 or 2 hertz. Now we have 50 means 50. Deviation allowed tolerance nowadays from a generation side is so low. It's like it has to be like 49.9996, 50 basically 50.0001. Like that's the tolerance nowadays. Like that hurts. That puppy is locked. Voltage, we do have some leeway, because be mindful, by a law, every equipment that you are using is designed, like it should be designed in such a way that it should be able to tolerate few percent plus and minus by design. Because again, nobody is stupid enough to think 110 means 100. No, it will fluctuate. No matter what you do, it will fluctuate. So it has to make sure this voltage and hertz remain in the safe limit. And they do look huge, like you can see that, like this is a pole, this is isolator, this is a dude, you get that, like these are huge, this look like so much powerful, but these are fragile AF kind of thing. So that's the problem. So we come to dispatch center. Now we reached a point where even small towns crossed a point where single power plant no longer can provide them. No matter how big they became, like they simply cannot. They're just like, no, I can't do this. So we reached a point where, and again, opposite also happened, meaning some small towns is like, bro, we can't have one power plant because you do not consume enough electricity. So we created a scenario where we had to connect a lot of power plants and distribute their power to a large community. And that created a scenario where we had to figure out how to balance it. Added power plants, making power plant, child's play. Balancing power plant, that requires dispatch center. Now, what is grid? So grid is made out of three components. Component number one, power producer, be it solar farm, be it hydro dam, be it nuclear power plant, be it whatever. That's producer side. Then you have interconnect side. This is the backbone of it, basically this puppy. That's the interconnect side. And then you have the distribution side, basically the people who take the electricity from this puppy and give it to you. That's what, these are the three core. And the brain of all these three are basically muscle. The brain is the dispatch center. Basically people working here or here decide what happens to you. Meaning they decide whether you get to turn on your electrical equipment or don't. So it's up to them. And not to mention, they are also responsible for the cost. Even though cost is levelized for you and me, they are directly dealing with the cost. Meaning, if they did their job quite well, meaning they are balancing cost as effectively as possible. Again, you cannot drop cost beyond a certain point. But if they are doing quite well, they're making sure they are being as cost effective as possible, it gives government enough money that they can invest in the grid itself, meaning they can make more interconnects. Because power plants, they are operated by private players. But interconnects has to be operated by something big, like a country. So in those sort of scenario, they are directly controlling the cost of it. If they are efficient, they are wise with it, you're gonna be like, hey, we had one interconnect, now you have 10,000 interconnects. That happens over time, of course. It not happens day one, but if they are good with the money, your country can grow. And they are the one deciding the basically uptime and quality. Uptime as in like, do they decide to give you low voltage, or do they decide to cut your power? It's up to them. So they also control the quality. Again, voltage, little bit of fluctuation is acceptable. Frequency, very little, but again, it does happen. They decide it whether it's acceptable or not acceptable. Those are very powerful people, like literally powerful people. So what are the vectors that they have to take into account? Well, every power plant, even though we say power plant, does not mean power plant. Power plant simply means data that gives you something in certain conditions. For example, you have nuclear. Now these puppies are bad puppies because they do not move around. They are like very static. They are puppies, they behave like an old dog and they do not change their power. And this is another reason why I hate nuclear power plant, is like they do not have off state, meaning again, anybody who understands nuclear physics, they know that even if you put control rods, shut down the power plant, it will need cooling for 2 years. That's why even the fuel has to be, spent fuel has to be kept in a cooling pond for 2 years. So they do not have off, meaning their auxiliary load is constant. Even in case of Ukraine war, all the nuclear power plants have to have DC generator working 24/7, because if the cooling flow ever stops, bad things could happen. Now, hopefully after like around few months, the temperature comes down enough where it's only going to damage the reactor rather than the building. And at that point, it should be quote unquote safe enough, but you get that point. Like these puppies are very static. They cannot go below a certain point. And that also limits their output. Meaning, in principle, they can waste power. In principle, they can just like cycle enough water with just to maintain it cool enough, drop down every controller, but they still need enough. So it's always advisable to run them as what we call base load, meaning do not change it. And because of the cost of it, it has to be done that way. So these, whenever they are added to the grid, dispatchers go like, okay, that's it. That's the bare minimum, let's say 2 gigawatt. That's it. Like this is 2 gigawatt on 24/7 into until it goes for maintenance or shutdown. So it's completely static. So that power producer is what we call base load. Then we come to another, coal. Coal is dynamic puppy. Now coal, while it does have a slow response, meaning it cannot just go, oh, you want more power, more power. It does not go like that. It does have hours. So meaning if you are suspecting that you're going to have power draw, let's say, because again, you are predicting everything, you can predict like once people start to leave their office, they're going to have a weak power surge, you can start to increase coal feed. That will increase the steam pressure, and you can start to, you know, build things up, build system pressure, and over time, once that surge happens, you're like, okay, steam valves go YOLO and you get more power. So coal is very dynamic and it can throttle their power from very low level to very high level. So this is static, that is very dynamic. Then we come to gas and hydro. Now these puppies are response, these are fast. So gas is the fastest because again, let's say there is a scenario where you know this puppy will take care of the load, but it is reaching there, it's gonna reach, let's say 1 hour from now, and you have over drain on the system. What do? You turn on what we call peaker power plant, or if you have hydro dams in your corn, you control hydro dams. These two things can throttle their power very quickly. Natural gas is like really responsive. Like it can respond almost like this, because again, majority of them are just jet engine, so they respond like a jet engine. So they're very fast. If they are startup and they are spooling up, in 20 minutes, they can give you all the power you need. So these are gas power. Hydropower, again, they also have their own data because they are working with nature. Nature could decide, hey, it's summer. In that point in time, your reservoir level could be so low that it's like, hey, if we open the full draw, basically full gate, we're gonna run out of water, basically safe level of water. So at that point in time, they can give you a red warning where it's like, bro, do not trigger full use. And again, in rain, it could be completely opposite. Please do not shut down the basically generators, because at that point, it will overflow the reservoir. So those data go into the dispatch center. That's the control vector. And then we add renewables to it. Renewables have their own basically curve to it. So the target of this experiment, so to say, is use the cheapest source first, meaning this is fixed load, so they will use it. But what about solar? Let's say they have giant wind farm and giant solar, basically giant coal plant, which they will use. They will use wind farm as much as possible. If wind shortfalls, then they will use this. But if opposite also happens, let's say wind is overproducing, they will shut down wind, but they will not shut down like the whole farm. They will like what we call power curtailment. They will shut down a few of the turbines that should bring the power down. And it does happen. That's why many times you will see wind farm and all the turbines are not working, and the turbines that are down does not have maintenance crew on it. There is a very good chance it is being curtailed. So they will basically dispatcher will always try to use cheapest source first. So in summer, basically hydro dam is not as cheap. So in rainy season, hydro dam first, nuclear fixed, coal second option, gas very expensive, but again very responsive. So they have to use it, but they are like very little as possible. So must use the cheapest sources first, and then you have to understand there are many reaction events, meaning whenever look something this big, this complex, where you have hundreds of power plant, thousands of customer, hundreds of kilometers of transmission line, but things will happen. bad things will happen, and they will happen 24 into 7 into 365. It's a constant deal. You will have a circuit breaker tripping, you will have a generator that is developing fault, sometime nature will make love to your transmission line, things will happen. So all those things will cause a reaction event, meaning if you're like, hey, this is a power plant, this is a consumption point, and this is a 100-kilometer link. Okay, here's the deal. Something bad happened here. Consumption is like, I'm down, I'm cutting off. But here's the deal. If you cut the power on the basically transmission line on this end, yeah, that generator is going a boom, boom. It's like, why the heck? We disconnected generator. Here's the deal. The line had capacitance. It acted as a super giant capacitor. It's going to flow back the current and increase the voltage. Now, generator will compensate as much as it can, but it will push too much stress. And many times, especially in very long cable, it can simply overwhelm the system. Now, hopefully, the generator circuit breaker will trip before generator goes boom. But you understand that. That's why you cannot just disconnect here. You have to disconnect from the generator first, then disconnect the transmission line. Then transmission line will over time fade the current. So fade the reactance, so to say. Again, it's a very complicated trigonometry, mathematics and all that jazz, but again, reaction event is there, and dispatchers have to do that. If they do not, they will fry some power plants. And all of these things are accounted for, meaning let's say scheduled downtime is a fixed thing, and they want scheduled downtime rather than random downtime. So they're like, okay, this line, we have to take it down for maintenance. So let's say it's tomorrow. What they're going to do is plan out everything today and be like, okay, grid will be in degraded state. What if something else goes down? They will plan out for it. They will like, okay, something bad happened, worst case scenario, we cannot get power from somewhere else. Okay, what else would you do? At that point in time, these loads are marked for emergency cutoff, meaning these loads are non-priority, shut them down. They have to do that. They have to do all the rehearsal and then they will take it out. Everything is basically planned for and accounted for. And how the heck they design like all that, like what the heck to do, what not to do? Well, predictions. They use prediction, meaning data consumption has been kept from like, as when the grid was basically interconnection began, they started to keep a record, and that record is the reason why we can even do this. That record gave us the data. It's like daytime you will have this much power consumption, nighttime this, and all that record have been kept updating, and then is getting trends. Trends is also getting amplified by events. Basically, you have sports event in India, like cricket event, it will change power consumption. You will have let's say New Year festival, it will change the power consumption. All that data go into this matrix of basically prediction algorithm, and that prediction gives that wise data output. Now that wise data output you will take, and generally that wise data is always conservative, where it's like, you know what, under no circumstances it should cross 500 megawatt of load at this point in time. So you will give that data to basically or the producer, and producer will must by law required to have 15% buffer, or again depending on some countries, depending on design, could even have 25% hot capacity, meaning if I ask 25% more out of you, you cannot bitch about it, you have to give that. So that extra throttle is always there. And grid can also do some compromise in some worst case scenario, because again, if given the choice of bad power and cut off power, bad power sometimes makes sense. So they can do some compromises, specifically voltage drop. Again, they have plus minus 5%, and hertz, they can allow it to drop to a little bit. Rather than having exactly 50 hertz, they can allow it to drop to 49.9996. So these are the vectors, these are the throttles that they are controlling. But if you're like, if this is this complex, how the heck they manage it? Well, they have a priority system. Priority system is that what should be must done first, like this cannot go wrong. So that is the basically grid must take care of itself. Grid must remain online all the time, no matter what happens, no matter earthquake, no matter what, no matter shutdown, no matter faults, no matter terrorist activity, it must stay online. That's the first requirement. And the reason for that is very simple. It's like, oh, why you cut power from a hospital rather than like, you know, power plant? Is like, if power plant ever goes down and the whole grid goes down with it, restarting it is not possible. Like you cannot just like, you cannot do that. It will take serious amount of engineering effort just to start this. Meaning many power plants cannot self-start. Majority of them require a small peaker power plant that turns on. Then you isolate that peaker power plant from all the consumer, send their power to big ass power plant. Then the big power plant turns on. Then that power plant triggers on all the other major power plants. That's how you restart a grid. It's very, very difficult. Because be mindful, auxiliary power requirement of big power plants could be as high as 3 to 5%. So imagine something that is 2 gigawatt, as in 2000 megawatt. What is 2 to 10%? Like you can't build generators that are that powerful. So like cost effective wise. So peaker power plants are used as a generator for these sort of system. But again, generally they won't be in the same location. So you have to create grid isolation. Basically isolate everything, load, and then just use this to trigger start. So fundamentally restarting grid is not a good go. So it must stay on. And if something bad happens, like this happened in Pakistan very recently, where the grid went down, it took them more than 24 hours to start that back again. And be mindful, their population is tiny compared to India. Imagine that thing happened to India or USA or China. Yeah, no. That restarting could take days. So it's very brutal. And all the links, basically every interconnect, every voltage line, everything must remain green, because while you can send over power or surge power through transmission line, it can only do that for short pulses, meaning it's like for 5 minutes in winter, I can handle some over my rated capacity, let's say 30% over my rated capacity. Can't do it continuously. You can't be like, okay, oh, this link is down, let's just send all the power. No, you have to figure out how to do that. And again, that's why dispatchers have interconnect with other things, meaning they're like, hey, we have to use either this line, and this line is already redlining, use some other interconnect or disconnect the power. Again, because if transmission line goes down, it's a much bigger hassle. So fundamentally, they always have to make sure that everything remains in the green zone. And power factor, line capacitance is another headache, because again, that's why AC does not go very far. We have to use DC whenever you have to send a power very far. And if you bury the cable, AC cable specifically, the capacitance goes up exponentially, and that becomes another hassle. So meaning anytime this dispatcher is like triggering on, he has to double check, is it an underlying high voltage cable? If it's an underlying voltage cable, he'll make sure how many generators have voltage absorption capacity, meaning power factor, leading, lagging, all those data will go into his computer, and it's like, I don't think the generator can handle. So it will create a scenario where reactor power caps will be absorbed. Then it's going to trigger it on. So capacitance has to be taken into consideration, because if you don't, surge back, boom, bad things happen. All that, and that's why they are preferring to add more and more high voltage DC links rather than high voltage AC links. AC links have very bad capacitance, and not to mention at short distance it makes sense to use AC, is cheaper, but at long distance like 500 kilometer, 1000 kilometer, anything more than 1000 kilometer, you have to use DC. Otherwise the capacitance will literally boom your power plant. And cost is the last factor. Ironically, like these are the people who only like, dude, make sure the grid is on, make sure everything is green. If you have time, worry about the cost. Like they are working on completely different perspective. They're like, dude, if grid goes down, money does not matter. If something goes boom, money does not matter. So all like they have complete freedom. They decide which power plant is used. They decide which cost to be paid. That's why cost is the last thing they have to worry about. So what we can expect in the future. Now, this is a very critical aspect. From these people's point of view, I have linked a video down below from 10 years ago. EV and renewables, that's not a big deal for them. Like, this is what their job is. This is their job. Like, hey, figure things out, sort it out. That's what they do, and that's what they have been doing for decades. They're good at their job. Do not worry about it. So from their point of view, all they ask of you, they do not care whether, oh, you are adding a lot of wind farm, it will create instability in the grid. They're like, dude, that's my job, I'll worry about it. And all they will ask of you is like accurate predictability. Now, like, oh, we can't predict wind and we can't predict sun. No, we can. You and I can't. But people, scientists, weather analysis, given the fact that we have launched 1000 plus satellites, we can figure it out. And surprisingly good, like horrifyingly good. Like this is an example of a graph that a power operator will get. The blue line is the projected graph. Based on this, the operator will operate things. And again, this will be designed as a conservative, meaning under no circumstances it should go down below. Now, as the early days of wind farm, this line was very sloppy, meaning you will have the actual power and it's like expected power would be like this, like they did not knew better. But as more and more data was collected, more and more real world data was there, this prediction became good. And like you can see that it's almost matching. The fact is, on large wind farms, it's damn good. Meaning, if the wind farm is 2 gigawatt, it will give you a prediction, accurate prediction, hour by hour, that is within tolerance of 1 or 2 megawatts. That's creepy that we are that good with wind farm. And not to mention, as the bigger wind turbine we make, taller wind turbine we make, the more stable it becomes. So, and the more and more wind farm we add, the more satellites data we have, the more throughput we have on the data, prediction becomes like, we're gonna tell you that we're gonna get 500 megawatt, that means you're gonna get 500 megawatt, done. And if you give them this, it's like, this is there, of course, they are designed by law to always have buffer capacity. They're like, I got this. They can take as much solar as you can give them, as much wind as you can give them. They will not even worry about it. And be mindful, I specified that nuclear power plant is ugly because again, it does not have throttle. That's why we developed pumped hydro. Pumped hydro was not developed for these. It was developed for nuclear in the 60s and 70s. And like late 80s, it was started to being deployed because everybody was like having nuclear fever back then. So they had the idea, it's like instead of making super large plants, which would be idiotically expensive and very dangerous, make small plants and they have continuous output. But again, you will not have continuous consumption. That power will be absorbed. Basically, at night, the overproduction would be absorbed by the pumped hydro. In daytime, it is going to provide the surge power. That's why pumped hydro was built. And again, if you have prediction data, pumped hydro, they can do 100% renewable without too much hassle. And again, if you need that peaker power plant, again, collect human poop, convert it into methane, voila. That's it's already happening anyway. So we're gonna convert that system sooner or later. And not to mention cow poop, super methane producer. So again, desirable. So from their point of view, this EV, this basically renewables does not matter. Like even the power draw of these puppies, it's tiny. From the fluctuation they manage on day to day, this is tiny. To give you a context, many countries have surplus power. So how do they absorb that surplus power if they do not have pumped hydro? What will they do? They will have direct line of communication with metallurgy plants, meaning the plants that are producing specifically aluminum. Aluminum consumes insane amount of power to make. So they use that as absorbers of basically of producing power. Nobody wants to shut down. They want to make money. But here's the deal. How do you absorb that money? You sell cheap power, again not that profitable but not loss. You sell cheap power goes into the power plant, you have cheap aluminum, country benefits, everybody wins. So from those point of view, oh, I'm adding electric vehicle, it's like, bro, does not even register. So fundamentally, do not ever worry about that. So if anybody tells you it's like, oh, it's gonna make unstable grid, no, we crossed that threshold, we crossed that. Like whole European Union has 20% solar and wind today, as in like 2022. So it's done. Like 2023, I'm pretty sure it's gonna cross 25%. So we do need one thing. We do need more transmission line. That they are very sure. It's like we have this structure. Basically, you are making a tree taller. What do you have to do? You have to make sure the stem is thicker. So we need that thick stem. Basically, transmission line. We have to add a lot more transmission line. And we're gonna do that anyway. This is one other thing. Oh, we have to build so many transmissions. Like we have been doing that for past 100 years. Back in the days, 1 megawatt is big deal. Now we do not even give a damn about megawatt. Like there are solar rooftop power plants that are 1 megawatt in capacity. So understand this. This is one of those things that's gonna happen. We just have to expedite it. It's like, oh, we are adding 3 lines. Let's add 30 if we want to be damn sure about future. And the development in terms of new technology, long range high voltage DC lines, and smarter logic. Basically, the tighter we make this prediction algorithm, the better it will be for dispatcher. So the future is solid, kind of. In this regard, it's quite solid as long as we can keep investing on transmission line, which we have been doing for 100 years. So I'm very hopeful about that. So this was my presentation on basically power dispatchers. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.